morning, everyone. I, Arya Dow, welcome you all on the behalf of Extramural Lectures team, IIT Madras, for a very special Ask Me Anything session from Madras to Mars by Dr. Bob Balaram. And to start off, I would like to invite EML student head Malavika to introduce our guest for the day, Dr. Bob Balaram.
Dr. Bob Balaram is an Indian-American scientist currently working as engineer for NASA. He completed his BTech in Mechanical Engineering from IIT Madras and went on to pursue his MS in Computer and System Engineering from Rensselaer Polytechnic Institute, New York. He also completed his PhD from the same institute. He has been associated with NASA for over 20 years and has led a team in developing a high-fidelity EDL simulator, which was then used in Curiosity and Perseverance rover missions. He's now working at NASA's Jet Propulsion Laboratory as a chief engineer for the Mars Helicopter project. Sir, we are greatly honored to have you with us today.
Okay, thank you for having me. So rather than give a formal talk, with slides and PowerPoint, which most people will fall asleep, I thought you can ask me anything, but you can ask me about the helicopter, you can ask me about NASA, whatever strikes your fancy. I'm assuming somebody is going to run a microphone as we. So we have about an hour, okay, and so let's get started. So feel free, any topic, anything. So who wants to go first? Okay. Wait for the microphone so that. I'm poor, not very good hearing. I'm old, unlike you guys.
So hi, I'm Samarjeet from Aerospace Department. So while considering like you were planning to make helicopter, so what were the factors you considered for the Mars? Like it has to start from the ground, so that some turbulence will be generating, and plus the environment around it. So
so let's talk specifically about takeoff.
Yeah.
Okay, because that's a whole very broad topic of what to consider. So one of the things that we were quite concerned about is how much dust we would kick up in the process. There was a little bit of an unknown. I mean, our best scientists, Mars scientists told us that there could be dust. And one of the things with the helicopters that you have to worry about is you can get dust entrainment. If you've seen some pretty cool videos on YouTube of some helicopters with lots of churning. So we were concerned about that. We did some testing. We basically, used some simulated Mars dust kinds of things, and we matched certain dynamic pressure that we were expecting to see of the flow on the ground. And we didn't think it would be a problem, but we wanted to be very sure. So one of the strategies we used, our navigation algorithms and our flight profiles sort of try to be robust to dust. So what we do is we very quickly take off from the ground. And during that initial takeoff, we do not rely upon our vision sensing. Normally, we use our downward-looking camera for a lot of navigation things. So for the first meter, 2 meters, we fly completely on inertial sensors. And so typically, when you get to about 1 rotor diameter away from the ground, the ground effects of dust and kick-up is usually very dramatically reduced. So the helicopter quickly flies through any possible dust, and then it starts using its full set of sensors. Same thing on the way down. As we start coming down, about a meter or two, meter and a half above the ground, we stop looking at using the camera because we don't know whether we're going to kick up dust, and then we land primarily on the just inertial sensors. Also, the other thing is that we were concerned about is there is a ground surface interaction. If you spend too much time in the takeoff, you can have some interesting mechanical interactions between the feet and the ground, and you can establish some unknown resonances. You might excite certain frequencies through that chattering interaction. So both at takeoff is we turn the collective, which changes the blade pitch angle, we shoot up, and on the way down also we land very firmly. We don't sort of try to come slow because we don't know both in terms of dust and in terms of any ground resonances that we can have. Now, it's turned out that at least in the places on Mars where we have been, we have done 31 flights so far, dust has not been an issue. But if you go on YouTube, there is a good video where one of the scientists, we got some accidental signs on dust transport. You'll see some dust entrainment and enhanced videos which show the dust as the helicopter is flying. So the dust kick-up is there, but it is not enough to really bother. But our flying strategy is robust to having dust. Wait for the microphone. So somebody.
One following question is there.
Okay.
So you have to also worry about the landing system, like landing gears
Right.
and all, right? So there also, like if you are doing that very quickly, then it should be that robust.
Right. So the landing system consists of one aspect of the landing system is how good does your guidance, navigation, and control deliver you to a state where you have a good velocity, good angles, good rate of angles. So that's one thing. But on the mechanical side, we have a spring damper system at the shoulder of the leg. So basically what the system does is there's a springiness, but if you just left it as springiness, you could have a bounce and things. So you need to have something that is a damper, which takes out the energy. So we thought long and hard about what kind of damper to use. So we ended up using basically an aluminum damper, where we actually yield the material into the plastic deformation. And it's the only part of the helicopter which is consumable. That aluminum damper in the shoulder is good to about 300 hard landings. But we never had a hard landing because our guidance, navigation, and control is doing quite a very good job. We did a lot of testing of all kinds of landing situations where high velocities, high sideways velocities, lots of tip rates and so forth. We have not actually had any landing like that. So I don't think the damper system has been affected. The main advantage of making the damper out of aluminum was it works very good at cold temperatures. One of the problems you have in any space mechanism is you really can't depend upon friction, because friction is very dependent on trace quantities of gases and volatiles, and so you can't predict exactly what the friction coefficient is going to be. So typically when you design space mechanisms, you'll have to sort of assume there's nothing or assume it's full friction. So it's really not you can't dial in a friction and guarantee that after exposure to space and vacuum, whether some volatiles will have gone away and the whole characteristic would have changed. So instead of using something like a friction damper, we use this aluminum damper. And it turns out that aluminum has very good yield properties even at low temperatures. So that was the solution to provide energy damping. There's also energy damping because our feet are shaped. So when they actually do, there is a display out. And so there is some rubbing between the feet and the ground, which also bleeds the energy. Somebody here. So yes, somebody has to run the microphone quickly. So yeah. Okay.
So my question was, how do you design something like the first thing which came to your mind after someone said that you build Mars helicopter or something? So how do you estimate the size? This should be the size. This is the mechanism which we should use. So can you?
Let me. So in our particular case, the size was really dictated by what available space we had on the Perseverance rover that could accommodate us. So we had to really constrain the footprint of the system to be as small as possible. And in fact, before we ended up on the belly of the rover, we were actually had some other locations which would have required us to fold the blades instead of keeping them. That would have added a lot of complexity to unfold before you fly. But at the end of the day, there is only so much space, so that set the diameter. So about 1.2 diameters, which is where we ended up, is about the maximum you could accommodate onto the rover. Now, once we did that, the question was, what is a good compact design that fits into that? And so it turns out that coaxial helicopters are very compact compared to quads and so forth. And also coaxial helicopters for the same projected area, disk area, coaxials are slightly more efficient because the top rotor sort of channels the flow for the second rotor. So it's a slight improvement in efficiency. There is a number called figure of merit used in helicopters to see how well you do in terms of energy consumption and things as a function of diameter and blades and so forth. So we got a very good figure of merit from going with the coaxial. We only had about 1.2 meters in space, so that fixed it. So once you know the diameter and you have a pretty good estimate of what the figure of merit will be, you can't push that too far because then you get into stall. You have to sort of operate, at a reasonable operating point, and you know the density. That tells you everything you need to know, and then you know how much thrust you can, it all gets sort of combined into that. So that was the constraint, basically size and compactness and slight considerations of efficiency.
And one follow-up question. The density of air at Mars is very less as compared to Earth, right? So how do you make sure that drone lands up upon Perseverance even after roaming?
No, we don't land on Perseverance. One of the things is that we are not allowed, for safety reasons, to ever come near Perseverance. Okay. So initially, we were not allowed to come anywhere within 100 meters of Perseverance. And since then, based upon our flight performance, we are allowed to come to about 60 meters near Perseverance as far as landing and takeoff goes. And of course, the concern is that here you have this multi-billion-dollar flagship mission, astrobiology mission, looking for signs of past life on Mars. The last thing you want is some stupid drone coming and crashing into it and causing problems. So we don't land anywhere near Perseverance. We are fully self-contained. The only link we have with Perseverance after we are deployed is we have a radio, and there's a mirroring receiving radio. There's a radio on a base. We have a base station on the rover, and we have a radio. So the only thing that interacts between us is the radio. Okay, somebody from this side. Or do we have one microphone or two, or is it just one?
Can you control?
Ask so that they can hear you. By the way, I don't want to let one person ask too many questions because then somebody will come back to you.
Control Mars helicopter from Earth?
It is controlled from Earth by sending waypoints. We send waypoints X, Y, Z heading, because the speed of light delay and everything is such that it's anywhere from 4 minutes to 20 minutes. Plus the operation cycles really allow us to only talk to assets on Mars about once a day. So everything is done autonomously by sending command sequences. Somebody from that side? Anybody? Okay, gentleman here.
I want to ask a question that why helicopter? Why not a UAV, or why not a fixed wing aircraft?
Okay, right. So in the past, I've actually done some studies on other alternative aerial vehicles on Mars at more at the study level, like things like balloon systems and so forth. Now, fixed wing planes have been considered for Mars. In fact, NASA had a pretty serious proposal, a mission called Ares, and another one called Kitty Hawk. Now, those were all designed to sort of fly along Valles Marineris, which is, the biggest canyon in the solar system. It's like Grand Canyon in the USA, but the entire width of the USA. That kind of canyon is a huge canyon. Fly along and take pictures, for example. The problem with any vehicle like a fixed wing vehicle is that in order to keep flying in the Mars atmosphere, you have to go by pretty fast. You have to maintain enough velocity. So you're just zipping by. A helicopter allows you to dwell, right? You can come and hover and look at things. So I can get to within, this distance from a cliff wall, where maybe there is some water coming from the side or something which we are hoping to find, right? And you can come and you can station keep and take the picture. That's one thing. The other thing is any kind of fixed wing aircraft, there's a whole issue of takeoff and landing. Now you can have some VTOLs which will transition from vertical helicopter-like flight, transition to horizontal, like, there's an Osprey aircraft that, for example, does that. But that's a complex sort of thing to do for the first time. So it turns out that helicopters don't need much in the way of airfields. As long as you can land within a reasonable area that you think is clear of rocks and slopes, high slopes and high rocks, you can take off and land pretty much anywhere. So ability to take off and land repeatedly without needing a prepared airfield, ability to sort of have dwell and look closely at things at very close proximity and station keep, those are the main advantages of helicopters compared to a fixed wing. And actually, helicopters can move quite fast. In the case of Ingenuity, we don't move at an airspeed. We tested in the wind tunnel that we built to about an airspeed of about 11 meters per second. So the actual vehicle, in terms of its absolute aerodynamic performance, could probably go about 20 or 30 meters per second. But we also designed our control system to be around the hover point. We did not want to do gain scheduling to try to develop controllers for different speeds. Plus, we would have had to test at those different speeds, which is difficult. So our hover controller is good to about 10 meters per second airspeed, 10, probably even more in tested conditions. We have tested it up to that. In simulations, it will probably be good to about 15 meters per second. But the vehicle of that kind of design inherently can go to about 20, 30 meters per second, which is pretty good. So you can travel quite a good distance compared to a rover for sure. You may not be going at Mach 0.7, like a fixed wing aircraft whizzing by, but all these disadvantages of a fixed wing, in terms of observing and doing science. So the helicopters are an obvious choice. You could also say, what about something like a blimp, controlled blimp? That is a possibility. There are problems with inflating those, inflation system, all those complexities are there. Plus maneuverability in winds and things is more of an issue. So, but not that it cannot be done. But at the end of the day, I think a helicopter is a pretty good choice. Okay, somebody from this side.
Yeah.
So yeah. And then who goes next? Let me then get somebody going from, now I want to go back. Okay, you'll be next. So I'll make sure the microphone gets to her.
Yeah, just assume I'm PM of this country. I'm asking you to set up a NASA here. You have to deny with reasons.
You have to what?
You have to deny the request with reasons.
Well, we already have a great organization called ISRO. So okay. You're living in the past. No, I don't mean, I mean that ISRO is a very, very good space organization. So you don't need a NASA here. You already have ISRO, and ISRO is doing great work. So don't think in terms of NASA and ISRO. In fact, NASA and ISRO have a mission coming up, joint mission. It's called NISAR, NASA-ISRO Synthetic Aperture Radar. It's going to do Earth observing with a synthetic aperture radar. So it's going to be really, really good Earth observing mission. In fact, I think the spacecraft's all integrated. It's going to come to Sriharikota for, I think, eventual mating to the PSLV and launching. So no, don't go there. You don't need to go there. Maybe 50 years ago, you could have asked that question, not today. Okay. Who's next on that side? Okay.
Hello, sir. I want to ask about that. What kind of flight controller of you have used? Maybe was it a PID or have you used some additional
right? So
innovative techniques?
Yeah. So there are different control levels. So right now at the motor control level, it's basically a PID control that controls the propulsion rotor, and there's a servo motor, the PID control loops. And actually, even at the higher levels, the flight control is a nested set of PID control loops. Now, they're not just simple PID loops. They have various loop shaping to get the best performance and best multivariable phase margin, gain margin types of performance. They have some notch filtering at places because at the rotor frequencies, there are noise in the system at the rotor frequency and the harmonics. So there's certain notch filtering in the control loops to sort of reject noisy data that we know will be there at certain frequencies. And so there's an inner attitude. So there's a motor controls where we basically run the rotor motors at constant speed. And then there are servo controllers which control the two swash plates. Each swash plate has both cyclic and collective. So we have some redundancy there. You only need one set of collective and cyclic. And of course, you need a collective on the other one to balance torque. Otherwise you can't just have it on one. But we have cyclics on both. So we have some redundancy. So 3 degrees of freedom in each. So that's totally 6 servo motors, 3 on the top, 3 on the bottom. Those are also PID control loop. Those are managed by our field programmable gate array, which directly controls these things. And then there is an inner attitude control loop, which basically maintains attitude stability. And then in a helicopter, if you give an attitude command, which basically tilts the vehicle, you get translational control because you get the thrust vector is now tilted and you move the vehicle. And so there is an outer translational control loop.
Hi.
And who's next here? Okay, you.
Can you throw some light into the powering of this helicopter? I hear, yeah. As I learned, the helicopter can fly up to 90 seconds or something.
Let's talk about that. So we harvest the energy from the sun in 2 ways. We harvest the energy in the solar panel, which charges a lithium-ion battery. We also passively, thermally, we have very high alpha coating. Any mechanical engineers here? Any of my friends, mechanical engineers here? Let me show my hand. Okay, good. We have a very high alpha coating on the fuselage so that when the sun comes in the morning, we get free heating from the sun to warm up the electronics. The energy in the battery is we warm up the battery to about plus 20 degrees C before flight so that the chemistry is nice and warm. We have tested our 6 lithium-ion cells. They're standard commercial Sony BTC4 cells, which we have tested it to about 550 watts discharge. We have typically will be only using about 300 something watts during flight, including peak power needs. And that is the power system. I think that's basically it. So it's solar, and now our solar cells are directly, is a direct energy transfer into the battery. So we have matched the cell substrate cell voltage to the cell. So we do not have a peak power tracker. So we are just riding the IV curve to directly, charge the battery. That's about on the power system.
And the motor,
So let's talk about the motor, the reason for the 90 seconds. So the propulsion motors are custom 23 pole pair motors, hand wound with a square cross section wire. Each motor took 100 hours to build under the microscope. And the reason we went with square cross section wires is for efficiency. You can pack more copper. So with round wires, you can get 91% or something. With square, theoretically, you can get 100% packing. So the problem there is that all the heat that is generated in the motor, the waste heat, right? Only some fraction of the electrical energy is converted to mechanical. That has to be absorbed in the motor. We do not have the luxury of a thick atmosphere, so cooling fins and things would not be able to dump heat quickly into the...
Was it air cooled?
No, it's not air cooled.
Not even.
It is not cooled at all. Okay. So what we do is the entire heat of the waste heat is absorbed in the motor housing. Okay. So in order to facilitate that, we actually make the motor out of a pretty exotic beryllium alloy called albumet. And that has a very, very high heat capacity. And if you exceed the temperature limits, primarily there are magnets for these 23 pole pairs, rare earth magnets, and they are glued onto the the motor housing. It's an outrunner type of motor. Okay. So at some point, the glue will achieve glass transition temperature and lose strength. Okay. So we don't want to have that. So initially we were very conservative, and we said like, okay,
the glue that was the limit. That was the glue. It had
that is the limiting factor. Okay. And we were playing it safe in our first few flights, and we said 90 seconds. We knew that it would definitely come nowhere near that. Okay. So, but then we had the opportunity after our technology demonstration to show our worth to the scientists. And that required a really long flight across this region called Zeta. So the rover could never drive across. The rover has to drive around. And they said, can you fly across there and look and see what rocks and things and geology you have there? Then we'll decide how much to go and so forth. So that was a risk. At that point, I was willing to give up my margins. Okay, and I said, okay, we're done with the technology demonstration. We have got all the data we need. Let's push this vehicle to see how far we can push it. And I knew that the temperature would go up. And my judgment was that we could go up to a little over, over 2 minutes, or type of 2 to 3 minutes. Okay. And since then, that's the limit we have set. So we basically are limited by the waste heat that we can adiabatically absorb into the motor housing. I see. Okay. Somebody on this side.
If you don't mind, just last question.
Sure.
So what was the percentage of throttle at which the helicopter is able to hover? And
we have about 30% thrust margin.
Thrust margin.
Yeah.
Okay. Thank you.
Yes. Excuse me, sir. I think I identified this gentleman here. No, here. And I want to go back and forth. Well, actually, there are less people there, so maybe we'll stay on this side for a bit. Okay.
Sir, the physical
conditions. Don't call me sir. I was never a sir. Just ask your question.
And the physical conditions are different on Mars and here, and pressure chambers can be of a limited size only. So how do you test it in a large scale?
Was it
the physical conditions, as in the pressure and other physical conditions?
Pressure. Okay. Yeah. So we have in JPL there is a space simulator chamber, which is about 8 meters in diameter and about 30 meters high. So we can evacuate their chamber completely and backfill it with carbon dioxide to the desired mass density. Dial in the density, which is basically pressure, so that we achieve Mars conditions. So that's why we did a lot of our flight testing under ambient temperature in this chamber. Now, we can also, in this chamber, flood the walls with the liquid nitrogen. But that is a very expensive thing. Like we did that once, where we wanted to make sure that as the temperature drops, the speed of sound goes down, right? Square root of t. So the Mach number goes up. So we wanted to make sure that even though our CFD modeling said we should be okay, we wanted to make sure that there was nothing unexpected that would happen as the temperatures dropped and the Mach number of the tips. We keep the tip Mach numbers down to below 0.7, okay? We want to make sure nothing funny happens. So we did one test, where we did use chill the chamber down to, not all the way down to Mars, but sort of halfway down, just to verify that it followed the trend line that we were expecting with lower temperatures. So that takes care of pressure and temperature sorts of effects. Then for gravity, we basically built what I would call as a high technology fishing line. So this is basically a constant force line, which pulls on top of the helicopter. Ideally, you would want that line to go through the center of gravity to compensate for Mars and Earth forces. But we can only tie it to the top of the helicopter. But using our simulation, we can understand exactly what additional effect that has of being offset a little bit. Still, laterally, it is not offset. It is mostly offset a little bit, vertically. And that pulls the system up and down with exactly the compensation, regardless of the motion. It pulls that forward. Basically, there is a torque sensor and the control loops that make sure that whatever the helicopter is doing, it flies with a little bit of extra helping force. Now, the first flight we did of a prototype, full-scale prototype, that vehicle was only 850 grams because the computer and the power supply and all of those things were under the floor. We ran a wire underneath. So at 850 grams, we could fly without gravity compensation. But for the full vehicle, we had to have gravity compensation. And so gravity, then we did environmental testing where we simulated effectively a day in the life of the helicopter. For that one, it was not a flying test. It was just to make sure that all the electronics and everything survived. So we went down to Mars temperatures, nighttime temperatures, and we came back up, made sure everything was okay. There was another test where we were actually bolted underneath the rover. And the rover does a week-long test where they go through a full, environmental testing of the, whether the rover survives. So we were part of that test. But we were just passive. We were just sitting there, just to making sure that nothing would happen. We were not flying or anything. We were in a undeployed condition. So we did that's called thermal vac testing, TVAC testing. We did flight testing, as I mentioned, with correct density, little bit of temperature testing on the flight. And then there were other environmental tests which are not really about Mars. There are things like pyroshock. Like in the rover, any deployment that you see, like wheels coming out and there's all big explosions are going off. These are pyrotechnic devices that go off. And you can get shock loads in the many thousands of G shock coming through the system. And so we did a bunch of pyroshock testing. We also did a lot of vibration testing because during launch, you can get, for something like the mass of a helicopter, there's something called a mass acceleration curve. If you go look at it for that size, there can be 60, 70 Gs of vibration loads. So we did a test on the vibe table where there's a shaker that shakes it to those comparable power spectrum levels. And I enjoy giving a talk where I can be technical, because normally when I talk to a general audience, I will not talk power spectrum and this and that. But yeah, so we match the power spectrum that the launch provider says is what they expect to see. And we see what that equivalent power spectrum of the vibration will be at our location. We do a vibration test. So those are not strictly speaking Mars environmental tests, but they're part of the spacecraft environment. We did radiation testing of parts before and selected parts that were radiation resistant. In some places, we did some mitigation by doing some current limiting to prevent single event latch-up and destructive latch-up of devices. What else? I think that's probably the extent of the sort of the environment-related test campaign.
So one more thing about the bottlenecking thing is your temperature on the motor hub. So why didn't you use an active cooling system?
Well, there's a complexity, right? So we did consider for a very long time whether to use a phase change material on the motor housing. In fact, that first full-scale model that we did in the chamber, the one that I said was 850 grams, we actually had to use some paraffin wax, type of phase change material to keep one of the electronics components cool, because we were using more of a commercial off-the-shelf, motor controller hardware. It's complexity, right? And it's mass. So the simplest thing was to adiabatically absorb the pulse, and by using albumet, we were able at a very, very high heat capacity. I don't remember the numbers. You can look it up, but it's much, much higher than your normal materials. And so we were able to absorb the heat. Okay, I think we should give
just
one last
question. About the battery, you said you use lithium ions, but there are more other batteries which have better energy density. So why lithium ions?
I think, well, first of all, there are more batteries that have come. I don't know what the specific technologies are available right now. We cannot have a vented cell. It has to be a fully closed cell. We were looking at both high energy density as well as high power density. We wanted to be able to handle the high power surges. Also, for this project, which was a technology demonstration on what in NASA terms is a shoestring budget, we did not have money to start a whole battery development technology to sort of custom make a battery. So we basically went to the market. There was a Panasonic battery under consideration. There was a Sony battery under consideration. And the Sony VTC4s worked out very well. They have very good energy density, very good power density. So they were perfectly okay. And the other thing that was very important during the entire battery thing was tremendous issues on safety. The last thing you want is the helicopter's battery to explode and, vent and cause problems for this huge NASA mission. So during the entire cruise, we keep the state of charge to below 35%, because we proved with a lot of short testing, we shorted the batteries. We proved that at 35%, there will not be any venting, okay? And even at 100%, the chance of venting is very small, but there was some test data that said, okay, we might vent. So all through cruise, except the very final moment before we were dropped off, we were allowed to go to 100%. So battery safety testing, whether they have, all the protection features in the battery test program. So if you start a new battery development or go with some other battery, you have to go through the whole thing. So at that time, there were essentially 2 candidate batteries and one, Sony is the one we picked. Okay, somebody back there. Yes.
Already a lot of technical questions. I want to ask, you did BTech in mechanical, then you shifted to computer science. Like, it's very unconventional.
It's not computer science. So, okay. I didn't do computer science.
Okay.
I'll tell you what I did, but ask your question.
Okay. So, can you share your journey till NASA? How you did, like, what was running through your mind and how you managed to
okay, this is going to sound completely I came to IIT with mechanical, not because I wanted to do mechanical. I was stupid enough at 16 to think getting a mechanical engineering BTech and an MBA was my ticket to the future. So I came there. I don't know whether they still have it. There was a committee that you come and you tell which IIT you want to go to. So first guy out was Kaushik Datta. His father was a professor here. And he said, I want IIT Madras. Okay, people understood, okay. His father had passed away recently, so okay, you want to stay with your mother at IIT. He was working, I think, in the library. Second man, me, IIT Madras, and they were shocked because at that time, all the top fellows who got good ranks went to IIT Kanpur to do electronics. So what is this stupid, what are all these fellows doing mechanical at IIT Madras? So very quickly, I realized I have no interest in MBA. So then I got really interested in 2 things. I got really interested in control systems. Okay, there used to be something called the Fine Techniques Lab here. I don't know if it still exists, but they do all controls kind of work in the mechanical department. And then I got interested in nuclear. So there was a professor here, Professor Shesha Shai. She did a nuclear also at RPI. And so when I wanted to do my master's, I said like, okay, I want to go and do nuclear. So I went to RPI, did my master's in nuclear engineering. And I joined, but it was a controls related type of thing. So it's controls and nuclear. Then computer and systems engineering, so focus on the systems part. So the control systems, I went into the robotics lab for my PhD. I switched from doing nuclear to robotics, and then from there, I finished my PhD in robotics, control, nonlinear control, and then I went to JPL where I worked on robotics, I worked on rovers, I worked on servicing robots, I worked on balloon system designs. I worked on high fidelity simulations, physics-based simulations for entry, descent, and landing. And eventually I had this idea for the helicopter, which eventually became Ingenuity. So no, I did not take some, oh, I want to do aerospace. There was nothing like aerospace engineering as a discipline back then. And as I said, I started off completely, I will admit it, I was thinking that the only reason I did mechanical is because I thought mechanical and MBA was like, but it proved very good to me because we used to have a 5-year program. And in the first year, I don't know whether they do it, every alternate week was workshop week. So 1 week of classes, next week you put on your khaki, a full week of workshop. And what first 6 months of workshop was all by hand, no machine shop, nothing. So the first assignment was like in the fitting shop. They give you a cylinder of steel, maybe 3 centimeters in diameter, 3 centimeters long, and file it down to become a perfect cube, okay? Perfect cube. So it has to be the right dimensions and all the right angles. And you can imagine in summer months, doing this out here, no air conditioning, nothing like that. But it taught me, and this is something that, was the German model of, education where you have to connect the brain to the hand, okay? And so what it gave me was an appreciation of what it takes to really build things. See, sometimes we get the impression that things just build themselves, You do something on a computer and something comes out, but actually there is a whole physics and a materials and a process that is, there's nothing automatic about it. You can make it automatic. So I found that mechanical engineering training invaluable, okay? Because as you can tell, building something like a helicopter, a lot of it is, it's everything. It's mechanical engineering, electrical, thermal, chemical, power, chemistry, planetary protection. There's a whole bunch of disciplines, but I was very well grounded in mechanical, which really helped, I think, in helping make, we had a lot of mass challenge, trying to keep the mass of this thing down, So even though I was not the expert in composites or the expert in stress or the experts in this and that and everything, I knew enough to have a good dialogue with the subject matter experts. So I knew what he was talking about. I knew what I didn't know, so I could ask, what I was not afraid to ask questions. So the mechanical engineering was invaluable, but that's not the way I started. I started because I thought it was that good combination with an MBA, okay? So that's my story. Next.
Hi, I'm Karthik. Sir, since it's a helicopter, it's very dependent upon the environmental conditions. How did you tackle the uncertainties in the atmosphere in Mars?
Right. So we commissioned a lot of modeling. We commissioned 3 types of models. There are global circulation models which tell you what the density profiles would be and some idea of the winds. But those are on large, very large cells, tens of kilometer type of cells. Then there are mesoscale models where there are a couple of university teams. Oregon State University was the one that we commissioned to do mesoscale modeling more for the local area, where the helicopter was supposed to land. We didn't know where the helicopter landing site was going to be till quite late in the mission. So we commissioned mesoscale models for about the top 6 candidate sites. So we had some idea what the density and wind profiles would be. And then the third type of simulations that we commissioned was something called large eddy simulations, which are very high, meter scale grids. And that really we want to try to get an understanding of the winds, okay? So that was the modeling that we did. And what we did after taking all of that, we also did a lot of Monte Carlo simulations with a physics-based simulation, right? So we could dial in, okay, the LES, large eddy simulation, and the mesoscale models indicate this. Winds will be from here to here, this kind of variation, this and that, this kind of vertical updraft, downdrafts. And then we put some sort of factors of margin, and he said, okay, let's run the simulated helicopter in this, see how well we do, and that kind of thing. So it's a combination of doing some large-scale, various modeling, and digesting all of that to put into a physics-based simulation that we can then exercise with Monte Carlo simulations. Okay, somebody from this side. So let's go all the way there. I don't want to neglect people there.
Even after so many simulations, did you actually encounter anything unexpected on the surface of Mars?
Okay. So that is a very good question. It was in fact a very pleasant surprise that we did not have any surprises. In fact, my chief pilot, we gave him the title chief pilot, but he's actually our guidance, navigation, and control lead. When he saw some of the first data, back from the telemetry, he processed the telemetry and he looked at all the data and he said, like, have I accidentally, plugged into one of the simulated data sets, or is this the real data from Mars? It was that good. And so the environment I talked about, but the physics-based model, first of all, is a multi-body dynamics model. Then what we do for the aerodynamics is we use airfoil models at different cross sections of the wing. So you have the basic, aerodynamic tables, CL, CD types of tables, and we build up the wing aerodynamics by slicing it up and having for each cross section, what the tables are. Those tables are derived from 2D fluent codes. We also did a bunch of 3D, CFD sims to verify that the 2D CFD is much faster. So we got those, and they were done for different, temperature, density conditions and things. So we got the aerodynamic tables that interacts with the multi-body dynamics model, and that, of course, the system has models for all the sensors and all those sorts of things. It's a full multi-body spacecraft simulation that we use at JPL for lots of missions. So we adapted that for helicopter modeling, and there really were no surprises. It was very pleasantly validated in that sense. So certain things that we were not sure of, for example, like how does the helicopter respond to side flow of a breeze? So for that, there are some coaxial rotor interaction models as to how that will happen. It's a little bit black art. So in that case, we actually put our helicopter in a wind tunnel. There was no wind tunnel in the US that could go down to both low density and low wind speeds, 10 meters per second, without some kludging, and we couldn't get time on that system anyway. So we built a wind tunnel. We put that into this big chamber I mentioned, 960 computer fans, open section wind tunnel. So we verified that we had the helicopter on a gimbal, and we were blowing air to see what the responses would be. So we verified all the modeling that we did were all verified with simulation. And the big part of the modeling is what we call a system identification program. So if you think about a system model, x dot equals ax, type of, what is that A matrix that really captures? X is your state, right? Position, velocity, attitude, rates, and all those things. So what is the A matrix? So by fixing the helicopter and measuring certain forces, by letting it be on a gimbal and measuring some other things, you can populate this A matrix, okay? So regardless of what the models tell you, you can actually do a system identification where you get the time series data from the experiment and you back out what the system matrix would be. And so we went through a very extensive system identification campaign in the chamber to actually really understand the dynamics of the system. And so with the dynamics fully identified, with good aerodynamic modeling, good environmental modeling, there were no surprises from the modeling sense. Okay, somebody in the middle here. Yeah.
How does the helicopter deal with the dust precipitation on the blades of the helicopter?
So the dust precipitation can happen in a bunch of places. The one that we were concerned most about was dust on the solar panel, okay? But on the blades, really, there could be some dust, which, because of electrostatics could stay on. But so far, we have really not seen any effect from any kind of dust on the blades. And we spin pretty fast, right? And helicopters are a very high vibration environment anyway, right? So it's not like it's, so anything that is above a certain size, I'm sure gets shook off by just the vibration. Maybe there is some thin layer of stuff that is still electrostatically clinging on, even at those high vibration levels. So we're not really concerned about dust on the blades, and it has not been an issue. We were concerned about a little bit about electrostatic charging as this blade cuts through the atmosphere. the Mars atmosphere, the dust has different charge particle, charges on the dust particles depending upon altitude and things. So we did some bounding analysis to make sure that we would not have electrostatic charge buildup. And there are effectively there are a number of ground, there are some conductive paths in various places to bleed off as much of the charge as possible. Somebody in the middle here.
Hi, could I ask?
Where, oh, okay.
Yeah. Firstly, since this technology demonstration was successful, so what would you like to carry out next, and do you have anything in mind for the future?
So NASA just recently, a few months ago, approved 2 more helicopters to Mars. So the plan, this whole Perseverance mission is to fill these tubes with Mars samples. Recently, I think there's a press conference, they've found some very high levels of organics. You don't know whether the organics are some other process or they from some life that may have existed, a few billion years ago, algae, mats, whatever, right? So the only way to find out is for those tubes to come back to Earth. So there is a mission towards the end of the decade where those tubes will be taken back to a Mars ascent vehicle, a rocket, which will then launch canister of tubes. And then there's a European orbiter which will rendezvous with that canister and then take that canister back to Earth, where we have all the highest tech labs to actually analyze the sediments very carefully and see whether it really was signs of past life or whether it was something else. So the primary path for bringing the tubes back is the rover itself. The Perseverance rover is expected to be quite healthy even, many years from now. So it will bring the tubes back to the Mars ascent vehicle. But if the Perseverance vehicle has any failure or it starts feeling unhealthy, feeling sick, then it will drop the tubes onto the ground. In fact, they're dropping a contingency cache of tubes on one location already. They're doing it. They're keeping the duplicates with them. But even later on, if they find that they're running into trouble, they'll drop more of the tubes. And 2 helicopters, what they're calling as Ingenuity class helicopters, will go and pick up each tube. Each tube is 150 grams. So they'll pick up the tube, one by one, they'll bring it to the lander, and the lander has an arm that picks it and puts it into the cache. So 2 of them for redundancy. And so the main difference is that these they look exactly like Ingenuity. We may operate it at slightly more aggressive operating conditions because now we have data. Like we may relax the 0.7 Mach number to be slightly more. We'll probably operate at a slightly higher collective because we have data and we're going to do more experiments to make sure. But the other big difference is that they're going to have 4 wheels instead of feet. So we can skid steer. So once we land and hop our way close to the tube, we can skid steer our way, drive up to the tube. And there's a small manipulator arm that will pick up the tube. Then we come back near the lander. We always want to land a little bit away from the lander for safety. And then we'll drive up and drop the tube top. So there is 2 have been approved. There is also a work ongoing to see what would a science helicopter look like. So since we have validated models for all aerodynamics, this, that, we know how to operate and everything, the thinking is that we could probably package a 30-kilogram helicopter into a pretty standard small aeroshell to keep it cheap. And that 30-kilogram helicopter, we're calling it a Mars Science Helicopter. It will probably be a hexacopter design. That's the leading candidate. Think of them as 6 Ingenuity rotors, which you unfold and you get a hexacopter. That would carry about 5 kilograms of science instruments, and it would be able to go tens of kilometers a day. And it'll also be more autonomous in the sense that we don't have to talk to a base station on a rover. We'll have our own radio to talk to an orbiter. So there is a Mars Science Helicopter that is being designed. There are 2 Ingenuity class sample recovery helicopters which have been approved. In fact, the team I'm sort of now an advisor role. I am not in the thick of it. I just sit in the back seat and I give advice. So those are the other 2 helicopters that are approved and are going to Mars.
Yeah. So since these are already so ambitious, if we remove the politicality or the administrative constraints and things like that, so just from the technology or engineering perspective, which mission would you like to take up, and just from the passion point of view?
I think
what would you like to pursue?
Well, one of the things that I'm interested in, especially with the sample recovery helicopters, we're sending them to Mars anyway. and their main job may or may not be to bring these tubes back, right? If Perseverance is perfectly healthy, these sample recover helicopters don't have anything to do, right? The tubes will be delivered by the rover, and but even if they are required and they are called upon to bring the tubes back, after that, they have two perfectly good helicopters. So one interesting idea that I've been pursuing is, can we encapsulate, I'm calling this concept as tube bots. These things are designed to carry 150-gram tubes. They can probably carry more. What interesting science or engineering or technology demonstration or something can you do in 150-gram things that can be carried by a helicopter? So you can imagine a helicopter which you want to pick up one particular tube, move it here, do some science. Maybe there's another tube that does something else. One of them is maybe a very high def camera, multispectral camera. Maybe one is some kind of sounding, bistatic radar. So I'm trying to think about architectures where you can have very modular instruments that can be carried by aerial vehicles to different places. You can do coordinated science, network science. So that's an interesting sort of idea in Mars, that these helicopters may have a life beyond their primary job of doing the thing. So that's one particular thing I'm pursuing. The other, of course, is the Mars Science Helicopter. There is a the issue there is not so much politics, but the way NASA funds science missions is through a competition process. So you have to have compelling science, and you have to be able to meet a sort of budget gap. But two very interesting ideas are, one is to explore the polar ice caps on Mars, to understand Mars climate and what it tells us even about our climate, right? We are conducting an experiment here with CO2 in this climate, but let us see if we understand what happened elsewhere, we can maybe understand better what happens here. There's another mission that is actually a survey of Valles Marineris, but with a science helicopter, not with a fixed wing plane like somebody was asking. So there's a bunch of Mars missions. NASA also has a mission coming up to Titan, and I'm in a sort of advisory role there. I attend their review boards and things. That's being run out of a place called Applied Physics Lab. So those are the things. So let's see, I think we have time for one last question.
Last question, sir. One last question. Could you talk about the role of AI, like ML algorithms in estimating some parameter, or RL algorithms in navigation systems?
No, there is no AI on any of this.
Any of this?
Nope.
Oh.
And the reason is, not being facetious, but anything that you build has to be validated. So the problem with, this is just a sort of a simplistic statement, but a lot of problems with AI kinds of things is, how do you prove that it will not do something stupid so a complex system is, difficult to validate. So that's kind of one of the reasons. The other one is that even though we have a lot of horsepower, we are carrying a Snapdragon processor, which is 150 times more powerful than the processor that's there on the rover, because the rover was forced to use old-fashioned processors because they're more radiation tolerant, rad-hard. It requires a lot of computing power, and computing isn't just computing. Computing translates directly into energy. Okay, so if I have so much energy, I can either keep myself warm or fly or run a processor for a long time, and it all comes down to energy, So similarly, somebody asked about control. We don't use any adaptive control for the same reason. It's difficult to validate. Okay, we don't send anything up that we cannot validate by some process, testing, simulation, and many of these more sophisticated techniques, while they will work, and if you're building 10,000 cars like Google or Tesla, fine, some of them are, killing a pedestrian one day, some of them are crashing, it's okay, you learn something from that. But how do you test when you're only sending 1 and 2 of these things? How do you test something to a confidence that you know that it will work? So there is no AI, there is no machine learning in any of the helicopters, or for that matter. Now, on the rover, they're using AI for other kinds of things, like there is an automated dust devil detection system. There is an AI system that looks at pictures constantly, and whenever it thinks it sees something like a dust devil, it'll ask the cameras to do some close-up photography for the atmospheric scientists. So in terms of pattern recognition, more passive, scene classification, terrain classification, people are using AI. But in terms of actually controlling the physical vehicle to actually do something, no, it's very well engineered, very well tested, highly validated, PID control loops and things like that. So the message is, think about validation along with the algorithm. Don't just blindly think that the technology, just because it can do something, how do I know, how can I prove that it can do certain things? Now, people are working on certain formal methods for proof and this and that of these systems. I think in the AI literature that people are looking at those kinds of things. But right now, I see it's more in sort of the classification, pattern recognition roles. But actually to reason and think and be autonomous and doing something, I'd rather have a stupid helicopter that I know if I tell it to do something, I know the parameters that it will live within, and I know how it might fail, and I can try to do contingencies for how it might fail. You give me this highly intelligent IIT Madras student sitting here and tell him to do something, will he actually do it? I don't know. He may go off and have tea at his cafe and not do the job, and it's the more intelligent a system is, the more complex it is to verify that it will actually do what you want it to do. So be cautious. Okay, thank you everybody. So thank you.
Now I would like to call upon the EML student heads and request Dr. Bob to leave a message for IITM community in the EML yearbook.
I'll leave a message. Okay. Oh, thank you. Then you got to take a picture?